Okay, so let's get right into it. For the longest time, the big news was just detecting the gravitational waves from two black holes smashing into each other. And don't get me wrong, that was revolutionary. But now, we're in a whole new era. We're not just spotting them anymore. We're starting to build a census, a kind of demographic profile of these cosmic monsters. And this isn't just about counting, it's about cracking the ultimate code. Where do they all come from?
And I'm not kidding when I say census. I mean, thanks to observatories like LIGO, Virgo, and KAGRA, we've got more than 150 confirmed binary black hole mergers on the books. That is a massive cosmic case file, and it gives us an unbelievable amount of data to sift through for clues. And that really is the central mystery here. It's easy to think that there's just one simple way the universe cooks up merging black holes. But what if that's totally wrong? What if there are multiple secret recipes at play, and each one creates a fundamentally different kind of black hole pair?
To start answering that, we're going to dive into the first huge clue from our cosmic case file. See, when scientists looked at all this data together, they noticed something, well, something weird. The universe of black holes isn't smooth. It's lumpy.
So, what does that actually mean, lumpy? Well, think about it. If all black holes were made the same way, you'd probably expect to see a nice, smooth curve if you plotted out their masses. Lots of small ones, fewer medium ones, and hardly any big ones. But that is not what the data shows. Not at all. Instead, it shows these distinct clumps and peaks.
And right here, you can see those lumps for yourself. This plot is showing the mass of the bigger black hole in every merger we've seen. And look at it. It is not one smooth curve. Instead, you see how the data clusters into these different colored regions? These aren't just random blips. They're the first really strong clues that point to different black hole families.
Which brings us to a really key term for this whole thing: subpopulation. The best way to think about it is like a biologist studying a forest. You don't just find animals, right? You find distinct species. You find bears and deer and squirrels, and they all have different traits and different histories. Well, astronomers are realizing the same thing might be true for black holes.
So how do you even start to profile these potential families? Well, one team of cosmic detectives took a very direct approach. They decided to sort all the evidence based on one key characteristic: mass.
Their method was super straightforward, but also really powerful. They just took the entire catalog of over 150 mergers, sorted every single one of them based on the mass of the primary, that's the bigger, black hole, and then they looked to see if other properties, like who they pair up with or how fast they spin, suddenly changed at certain mass cutoffs.
And what they found was wild. Their method pointed to not one, but two clear transition points, splitting the entire population into three distinct families. First, you have the lightweights, subpopulation A, who aren't picky and will pair up with partners of all sizes. Then you have the middleweights, who prefer to pair with equals. But then you get to the heavyweights. They like smaller partners, and most importantly, their spin is dramatically different.
And honestly, that last point, the spin, that's the real kicker here. It's the most dramatic difference they found. For black holes below about 40 times the mass of our sun, the spins are pretty consistently small. They're just not rotating all that fast. But once you cross that 40 solar mass line, something fundamentally changes.
And this chart just makes it crystal clear. That bright peak at the bottom shows that the lighter black holes are all sharply clustered at very low spin values. But as you move up into those heavier masses, that magenta curve, whoa, the signal spreads way out. A huge fraction of these monsters are spinning much, much faster. It's a dead giveaway that they were probably born differently.
Okay, so that was one team's approach. Now, another team of cosmic detectives came at this from a slightly different angle. Instead of just searching for breakpoints in the data, they started with a hypothesis. They asked, what if there are two completely distinct black hole gangs out there?
Their idea went something like this. What if the universe has this huge population of smaller black holes that follows what's called a power law? Think of it like a giant city, with tons of tiny studio apartments, fewer medium-sized houses, and only a handful of giant mansions. But then, alongside them, there's this second, much more exclusive Gaussian glub. This is like a planned suburb where all the houses are pretty much the exact same size, all clustered around an average of 35 solar masses. This whole hypothesis led them to a fantastic question. If these two gangs actually exist, do they interact? Do black holes from that big, common gang ever merge with members from the exclusive, massive club? Or do they just stick to their own kind? In other words, how much do they mix? And the answer from the data was striking. There is almost no mixing. Just the tiny 3% of all the mergers we see are mixed events between the two gangs. In fact, it's actually more common for two members of that exclusive, massive gang to find each other and merge. They really do stick to their own kind.
So what does this tell us? It tells us that these two groups are pretty much leading separate lives. And the fact that they don't really mix is a powerful, powerful clue that they likely form in totally different environments or through completely different processes.
So where does that leave us? Let's just step back for a second. We've looked at two separate investigations that use totally different methods. One sorted the data and found 3 families. The other proposed 2 gangs and found they don't mix. What's so amazing is that they both point to the exact same consistent story.
Both studies are telling us there is no single recipe for making black holes. The universe has a bunch of different ways to do it. And both investigations zoom right in on that group of black holes around 35 to 40 solar masses as being really, really special. They have different pairing preferences, they have different spins, and they seem to form this exclusive club that just keeps to itself. And look, this isn't just some neat idea or a wild guess. As the first team of scientists put it, the statistical signal is now so strong that the presence of these distinct families appears to be real. With every new gravitational wave we detect, the evidence for this complex, lumpy universe just gets stronger and stronger. So we've identified some key suspects and their behaviors in this giant cosmic detective story. But like any good mystery, the case is still very much open. So what does this all mean for the future? Well, the truth is, this investigation is really just getting started. Our gravitational wave detectors are getting more sensitive with every single observing run. And that means our cosmic case file is about to get a whole lot thicker, giving us even more data to refine these profiles and sharpen the picture of these black hole families. Which leaves us with one final, pretty tantalizing thought. We found solid evidence now for at least 2 or 3 distinct families of black holes. But as we get better at peering into the gravitational wave sky, what else are we going to find? What other strange black hole families are still hiding out there in the dark, just waiting to be discovered?